So today I will be presenting how processing influences the structure, which in turn influences the properties of thin film titanium disulfide. There we go. So first, background and motivation. Titanium disulfide is a transition metal dichalcogenide, which is a family of materials which have the chemical structure of MX2, where M is one transition metal and X is a chalcogen atom. And the most common polytypes of these exist in the 1T or 2H structure. And so right here we have a picture of the 1T structure, which is the octahedral, given that the transition metals are within these octahedral polyhedron. And we note that especially whenever you look at the top down, that the chalcogens occupy like each vertices of this little hexagon that we have here. Whereas whenever you look at the 2H structure, the trigonal prismatic, then they do not. So it's every other vertex of that hexagon. And this is due to the aligning of the chalcogens in the z-axis for the 2H, whereas they're actually offset within one unit cell, like one plane of the 1T structure. Titanium disulfide is typically observed in the 1T, and so that is what we will be looking at today. And this family of materials is interesting due to its 2D properties, meaning that they exhibit van der Waals forces in between the layers, which are easily exfoliatable down into thin film and even monolayer format. And in addition, they are tunable materials in that the electronic, magnetic, and mechanical properties can all be changed just based on the height of the material, the doping, or even the point defects present. And in the case of titanium disulfide, it was the first electrode for lithium-ion batteries, and the possible applications of thin film titanium disulfide extend into ion batteries, surprise, surprise, solar cells, spintronic devices, and many others as well. So this exfoliation can be done either bottom up through, for example, physical vapor deposition, which is usually done in either an evaporation-based system or a sputtering-based system. And in addition, you also have the top-down approach, which is what we will be covering today. And so you have this liquid phase exfoliation, which is the process of overcoming weak van der Waals forces in between the layers through some external stimuli. And so we will be looking at one paper which analyzes molybdenum disulfide, and then using this sonication to separate the bulk into thin films. And right here, even though you use graphite, the paper itself that we're looking at is on molybdenum disulfide, which is a TMD. And so the parameters for this are 127.5 watts for 2 hours. And then it is centrifuged at 8,000 rotations per minute for 20 minutes. And then you also have this laser-based exfoliation method, where you have the laser, which is incident upon your solution of material and distilled water. And in this case, you have to be a little careful, because if you have the laser at too high of a power, then you can actually induce point defects within that sample, which may or may not be beneficial. And now we look at how the structure influences the properties. And so this paper analyzes titanium disulfide through Raman spectroscopy. And Raman spectroscopy is, you have an incident electromagnetic wave of a specific energy, which is then absorbed. Some of the energy is absorbed through the material within these vibrational modes in between the atoms in the lattice. And then you are measuring that change, and so essentially what is being absorbed there. And that absorption is represented with this Raman shift in inverse centimeters. And so what we find here is that you have the EG modes, which represent the in-plane modes. And whenever you look at the single layer, bi-layer, 4-layer, and then 5-layer systems, you note that these are offset. And also that this x-axis right here is not incredibly well resolved. And so if you were to zoom in, it would probably be more apparent to you. But even then, you do notice that there is a shifting of this peak. And then you also have the A1G, which represents the out-of-plane peaks, those vibrations. And while these are a little bit more difficult to distinguish, you find that with the curve fitting, that curve that they're fitting is different for each one. And so that's another way of analyzing the thickness of the material. And this is often like one of the premier ways of measuring the height of your sample, but also illustrates how the structure will impact the properties. And now we look at how strain can impact the electronic structure. And so this study is on titanium disulfide and is theoretical, so it's density functional theory based. And what we have here is our general strain formula. So you take the resultant length minus the initial length over the initial length times 100%. And in this case, our initial length is 3.418 angstroms, which is the lattice parameter for titanium disulfide. And it's also important to note that all the strains are biaxial and tension loaded. And so they are acting to separate the layers from one another. And so to increase that van der Waals gap. And what we find is that before applying any strain at all, you get a very small indirect band gap right here of 0.01, or 0.07 rather. And then whenever you increase it, you find that there's a bit of a threshold or a maximum where you get up to the 6, 8, and then 9%, and they're all roughly the same. Whereas whenever you increase from 0 to 6, you get drastic differences. And eventually, you turn it from an indirect band gap into a direct band gap, which is also very interesting. And so now we go into the results that we have for the point defects that can occur within titanium disulfide and analyzing these and the resultant electronic properties. And so these are a combination of density functional theory and scanning tunneling microscopy based. And so you get a nice blend of experimental and computational. And so the parameters for these DFT calculations are all displayed here. And if you want, you can look at them. But essentially, these are all done with a mother compound of 3x3x1 unit cell, which is shown right here. And also defining our point defects. So we will be analyzing the pristine cell, the single titanium vacancy, single sulfur vacancy, the single add atom, the titanium interstitial, just one, and then the single sulfur interstitial. And interestingly, you'll notice that the atoms will be shifted even within that lattice. And so this is a result of the geometry optimization which occurs within the calculation. And what this essentially does is it finds the ground state of the system. And what you'll find is that the pristine does not change, given that those values were already experimentally determined. However, whenever you add these add atoms, and especially these interstitials, the atoms will shift around. And so specifically, we look at the single titanium interstitial. And while this was initially right here in that plane of titanium atoms, the titanium, they all have 4 additional electrons, and so they're not going to bond incredibly strongly, especially relative to how they'll bond with the sulfur, which has that -2 oxidation state. And as such, you find that the titanium is going to settle right on top of that sulfur plane, such that it can maximize the attraction between the titanium and the sulfur and minimize the repulsion between the titanium and titanium. And even then, you notice that some of these inner atoms are shifted around. So for the sulfur vacancy, you find that these titaniums are shifted, and especially the sulfur interstitial is a little funky. And so real quick, last piece of methodology here. And so looking at this diagram on the bottom left, you'll notice that we have a pristine +2, and then we have our add atom interstitial, and then our vacancy regions. And this is done because the total energy is determined by the sum of the intrinsic energies of the atoms as well as the interactions in between them. And so to keep one of these terms constant, we will use the same amount of atoms to keep that intrinsic energy constant. And so we are only really comparing the interaction energies. And so we do this by having our 3x3x1 unit cell. And then we have a vacuum spacing, which will include an additional titanium and sulfur atom. And this way we can simply shift those atoms around to fit the system that we're analyzing, the point defect that we're analyzing. And as such, this is technically more of a study on the formation energies with available titanium and sulfur atoms, at least within the environment. And so if you just have it in air, then it might act a little differently. And so these results do take some interpretation. And so now we look over to the actual results, which is we have our graph right here, where we have the defective system's energy minus the pristine plus 2 energy. And given that all of these values are negative to begin with, you'll find that the most negative value here will represent the most likely to occur point defect. And so titanium interstitial is by far the most likely. And you'll also notice that the vacancy, so the titanium vacancy and the sulfur vacancy, are both positive values. And as such, you wouldn't necessarily expect them to exist too often, which we will cover a little bit more with the experimental slide. And so now we go into how these point defects can influence the properties of the material. And so we look at the titanium interstitial, which is the most favorable of adding any additional atom to the system. And so we compare the pristine band structure, which has a band gap of about 0.334 electron volts, at least in that direct band gap direction. And what you find is that the Fermi level, so it's defined as the highest energetic state of any occupied electron within the system, is that rather than being in this little vacuum of space where there are no bands present, the Fermi level actually shifts up into the conduction band and will settle right in there with all these titanium 3D bands. And what this indicates is that the system is shifting from a semiconductor into a metallic system, given that you then have this highest energy electron that is occupied already within this conduction band and the conductive region. And now we look at the sulfur vacancy, which is the most favorable vacancy that we've analyzed. And we have similar results where you go from your semiconducting system into a metallic system, although this one is not quite as metallic, given that it is still sitting in the conduction band, but not quite as firmly as that titanium was. And these make sense given that in both scenarios you're increasing the ratio of titanium to sulfur. And we know that titanium is going to be more conductive overall. And as such, it makes sense that these would transition from semiconducting regions to metallic regions, just based on the shifting of those ratios. We now look at the experimental results, which are right in the middle here. So these are the STM images with the DFT comparisons on the left and right hand sides. And real quick, so STM is done in ultra-high vacuum. And what you have is essentially a pseudo current where you have, or pseudo circuit rather, where you have a tip and a sample, which are not directly touching, but they have a bias, an opposite bias applied to each one. And in our case, we have a positive bias applied to the sample and the negative on the tip, such that these electrons will tunnel from the tip onto the sample. And this is regulated by a constant current, which is set as a parameter by the user. And so what happens is whenever you scan over a more conductive region, which are these brighter spots, then there is a higher probability of tunneling. And as such, the tip will have to back away from the sample just to keep that, maintain that constant current. Whereas whenever you have a less conductive region, then the tip will come closer to the sample. And so, given that we have electrons tunneling from the tip to the sample, then these electrons are more likely to tunnel onto the positive regions. And since we know sulfur has the oxidation state of -2 and is looking to add electrons in its valence shell, then we argue that these brighter spots will represent the sulfur atoms here. And so what we have in these DFT electron density images is we have a 2D cut plane right in between the titanium and sulfur layers. And so these are going to represent the sulfur atoms. And what we find is that through the titanium interstitial located right there, and then the sulfur vacancy, that these represent regions such as this one, which indicate a vacancy, and regions such as these brighter ones, which indicate additional titaniums given the additional electron density available. And in addition, we did mention earlier that vacancies are not predicted to occur given our methodology and our results. However, these samples were annealed prior to the scanning, and as such, that additional energy could be the catalyst to cause these less likely defects to occur. And regardless, when scanning, we pretty certain that these are vacancies. So yeah. Oh, here we go. And just to wrap things up, so we conclude that titanium interstitial and sulfur vacancies are the point defects most likely to occur based on the DFT and the STM analysis. And in addition, we show that these point defects will influence the local properties of the material. And so relating to that processing impacting the structure, impacting the properties. That is the theme of this presentation. And our future plans, including submitting this paper for peer review and hopefully getting published. And in addition, we look to analyze magnetic contributions of titanium clusters and then compare that to already taken squid data, which suggests that these titanium cluster point defects would produce a magnetism in an otherwise non-magnetic pristine sample, which is very interesting. So also here are the titles and links to all of the papers that I've referenced today, just in case you want to check those out.